Hello everyone, welcome once more to our YouTube channel. So today we are going to be looking at r.m.s 2023, of course beginning with the physics. So we'll split the exams down into tiny episodes so students can go through each one of these episodes and really get to grasp the lessons and concepts there are in there to learn as they get ready for their GCE exams. Let's dive in. Alright, so just before we dive in, guys, this is our video outline, right? Because it's a series video. So episode 1 is going to be paper 1, question 1 to 13, episode 2 14 to 26, all the way to episode 12. So physics r.m.s 2023 is going to have 12 episodes, paper 1, paper 2 combined. All right, let's start with paper 1. All right, so question 1 says, which of the following set of quantities contains two vectors? A says torque, which is a vector, pressure, which is a scalar, surface area, which is a scalar. A is off. D is speed, which is a scalar, surface area, which is a scalar, and moment, which is a vector. D is off. C says moment, which is a vector, pressure, which is a scalar, and electric field intensity, which is a vector. So C is the correct answer. But B says magnetic flux, which is a scalar, torque, which is a vector, and electric field intensity, which is a vector. So B and C are correct. Now, B would have been wrong if the examiner said magnetic flux density. All right, this must have been one of those errors. So if it's magnetic flux density here, then B would have had all three vectors, and that would not have been the answer because we need just two vectors. So let's talk about why magnetic flux is a scalar. Okay, so first let's define what magnetic flux is. Magnetic flux linking a surface S is known as the total magnetic flux density passing through it. All right. We can mathematically write that as phi, which is magnetic flux, to be equal to the integral of the magnetic flux density across a particular surface. All right, so we are calculating the flux that is linked to that surface, so we get the surface integral of flux density. Now if we go over, before I just go over, just notice that this is a dot product here. We're integrating a dot product here. All right, so you realize that this result of this dot product already gives you a scalar. Okay, when you get dot product between two vectors, the surface vector and then the magnetic flux density, it gives you a scalar. Now that's basically the difference between work. That's why work is a scalar and moment is a vector, because work again is a product of the force and the displacement in the direction of the force, which is a dot product, and then moment on the other hand is the cross product between the force and the perpendicular distance from the pivot all the way to the line of action of the force. All right, so cross product will give you vectors, dot product will give you scalars. Across an area, the flux linkage would be the area integral of B, which is a scalar. All right, another way of thinking about B is basically the number of magnetic field lines that are going through a particular cross-sectional area. Are we together? So number of field lines going through a particular area. Listen, number of stuff in physics are usually scalars. Think about charge on an object. So it's the number of fundamental charges that are constituted in that object. Number of, that's why charge is a scalar. All right, so anything you can associate it with a certain number in physics is usually a scalar. All right, so that's why flux is a scalar here. All right, so I just need to explain why that is an answer. And so here we have C and B as the answers. Then we have question 2. When ice at 0 degrees Celsius melts to form water at the same temperature, which of the following is correct? Okay, first off, guys, you need to be smart. You need to notice here that we are doing change of state, ice moving from solid to liquid, all right, at the same temperature. So what does it absorb? Latent heat of fusion. You have to be very clear with that one. So the answer already is B. Okay, but let's just talk about why A, C, and D are wrong. Why is work? Why do we say work is done by the system? The statement is wrong. Okay, let's show you. Now, work done is basically P delta V. Okay, now since the ice contracts when it melts, of course you understand that that's one of the abnormal behaviors of water. So Vf would rather be smaller than Vi because it's contracting as it's melting before it gets to 4 degrees Celsius, and then if you keep heating it from 4 degrees Celsius, then it begins to expand. Okay, so we are realizing that W would be P changing V. Now V final minus V initial would mean that this difference that is negative. Why? Because V final is smaller. It has contracted as it melted. So this work done is negative. In thermodynamics, whenever work is negative, it means that work is said to be done on the system, not by the system. All right, so work is likely to be done on this system, and so A is off, and that is why C is wrong, because C says no work is done on the system, but there's actually work done on the system because the system contracts as it expands. Okay, so C is wrong because it says no work is done. Now let's see why D is wrong. D is actually wrong because the internal energy of the system, it says internal energy of the system decreases, but listen, internal energy is often tied to change in temperature. You are occurring, this thermodynamic change is occurring at constant temperature. So you notice that, well, internal energy would be bound to stay the same in this particular case. But when you get to college and you study solid state physics, you notice that it's a lot more complicated than this, and you get to understand that, well, internal energy can actually change in that system. All right, so in high school we'll keep it at this. So the work is done on the system. All right. However, to melt at constant temperature, ice absorbs heat from the surrounding. That's what we've talked about now. What's that heat? Latent heat of fusion. So we can define that the heat absorbed from the surrounding to change the state of a unit mass of ice to water at constant temperature is known as its specific latent heat of fusion. All right. And then you go over and then you talk about, well, and the heat absorbed by ice to change its state to liquid at constant temperature is its latent heat of fusion. Notice that there is no unit mass. All right, this unit mass is not here. So if you take away this unit mass, you'll be defining just latent heat of fusion. If you put the unit mass, you'll be defining specific. All right, so notice the absence of unit mass of ice, as this is only used when defining specific heat. So you only use unit mass when you're talking about specific something. For instance, specific heat capacity, which is the heat absorbed to change the temperature of a unit mass of a substance by a unit change in temperature. Again, unit mass. Are we together? All right, so I'm just like having time so that we can talk about the questions and do like in-depth revision of the physics paper that maybe was taken in the Southwest Mock this year. Let's go. The answer here is B. Figure 1 shows a potentiometer circuit. Which of the following is correct? Okay, the circuit can be used to measure rapidly changing temperatures. That's not true. I've just displayed a circuit here for you. The only circuit that can be used to measure rapidly changing temperatures is, of course, the thermocouple. All right. You can notice the differences in their ends. So there's the reference end, which has a known temperature, and then there's a measuring end. So you place an object here whose temperature is rapidly changing, you'll be producing a rapidly changing V out. All right, and so you can follow up with that. You can measure the temperature of this rapidly changing object, because, well, each time the temperature changes, it sets up a different V out. Okay, perfect. So this guy does not do that. For the balance length to be obtained, ED must be changing during the experiment. If ED is changing any potentiometer, I was going to say thermocouple system, well, in a potentiometer circuit, if this guy is changing, you're never going to get a balance point, because balance point, of course, I'll just do the maths later. I'll show you. If no balance length is obtained, then the wire AB is non-uniform. No, even if the wire is not uniform, you can still get a balance point. All right, balance point is basically the point where PDAC is basically equals to the EMF along this path. So yeah, you're good. The circuit can be used to compare the EMFs of two cells. Correct. Okay, let me show you how. If you come over here at this particular point like that, if potential gradient along this potentiometer wire AB is K, that is the potential per unit length. If it's K, then this EMF is balanced by a certain potential K multiplied by AC. Of course, ignoring this resistance. All right, because if this resistance is there, then part of this EMF will be dropped across this resistance, and so the balance EMF here should be less than this ET. All right, so we'll not talk about, because I just want us to ignore this a little bit. So if you get over where K is a potential gradient across, so you have EX. Now if I bring in an unknown EMF and I place it here, it's going to give me a new balance length at X. So AX now multiplied by the potential gradient equals the EMF of that unknown. So this equation 1 and equation 2, if we ratio those equations, then you notice that we'll get EX over ET, which is KAX over KAC. That gives us an expression where we are relating and comparing the two EMFs, EX, the unknown EMF, and ET, the known EMF. All right, as their balance length gotten from the potentiometer wire. Yeah, so this can help you to measure or compare EMFs. So the answer is D. when two bodies P and Q are in thermal equilibrium with each other, it implies that, well, it implies that the two bodies are at the same temperature. So obviously B is the right answer. But I mean, there's some things that I want us to see here. So thermal equilibrium merely implies that both the bodies are at an identical thermal potential signified by temperature. Okay. As such, there will not be any net, guys. I've highlighted and underlined that net exchange of energy via any of the modes of heat transfer. So there's no net energy exchange, but there is energy exchange. Okay. While heat flow is dependent on temperature difference, heat content of a body is dependent on mass and heat capacity. Therefore, it is possible for two bodies to be in thermal equilibrium but have different heat content. Since thermal equilibrium is a function of the temperature difference between two objects, okay, it's possible that two bodies with completely different heat contents can exist at the same temperature. Let me show you an example. The ocean, right? The ocean and your hot cup of tea. The ocean is at a lower temperature, but it has more energy. Why? Because the heat content of the ocean is a sum of all the kinetic energy and the potential energy of every molecule that makes up the ocean. That is the internal energy of the ocean. So you recognize that, well, it's a function of the mass and the heat capacity. Okay, so it has a higher heat content even though it exists at a lower temperature. So yeah, that just has to be clear that two bodies can exist at thermal equilibrium even if they have different heat contents. Because again, equilibrium is a function of temperature and not heat content. It is important to note that objects can reach thermal equilibrium without being in contact, in this case via radiative heat transfer. So yeah, that's all I needed to say here. So you can take note of, you can take down notes, you can take lessons. So the answer is B. Which of the following electromagnetic radiations is diffracted most on passing through a narrow aperture? Listen, diffraction is a wave phenomenon. The guy with the longest wavelength will be diffracted most, as simple as that. But I've given some notes here. The electromagnetic spectrum above is arranged from lower frequencies to higher frequencies. Lower frequencies, okay, means that longer wavelength. Low energy to high energy. Of course, if your frequency is low, it means that you have a low energy, okay. Radiations with longer wavelengths tend to exhibit wave properties more, while those with shorter wavelengths exhibit particle properties more. For instance, some of these radiations are able to penetrate objects. That is a particle thing to do, right? You notice that the guys who are mostly penetrating are guys with a very short wavelength, like gamma, X-rays. In fact, X-rays, they are able to penetrate your body, and even so that the nuclear magnetic resonance imaging can be able to distinguish between tissues in your body. That's because X-rays is also able to penetrate your body. All right, so these guys are very penetrating because they behave more like particles because they have a very short wavelength. The guys with very long wavelengths will behave more like waves. So diffraction is a wave phenomenon here. So radio waves will be the most diffracted, and then microwaves will follow, and then you have infrared, and then you have, and so on and so on. So you're just going. All right, so our best answer here is C. All right, the wave with the longest wavelength diffracts most. 6. A sinusoidal AC of root mean square voltage 10 volt is applied across a 50 microfarad capacitor. The peak charge on the capacitor is, well, Q is CV, right? So we have that Q naught will be CV naught. That's peak charge will be equal to C multiplied by peak voltage. So peak charge will be C is 50 microfarads multiplied by peak voltage. Peak voltage is root mean voltage multiplied by root 2. All right, so you have that as your peak charge, and our answer is C. So which of the following is an advantage of alternating voltage over direct voltage? All right, let's just talk about this a little bit. Let's talk about transmission systems. Now I want to transmit a certain power, PT. All right, that transmission power is of course I multiplied by V. Now, but wasted power along the transmission lines is I squared R. All right, so if R is the resistance per unit length, and then let's say you are using 5,000 meters of wire to transmit power maybe to a local community, that means that you would be losing I squared r multiplied by 5,000, because resistance r here is resistance per unit length, and that's a huge amount of power to waste. So what transmission stations really want to do is that they want to lower this current, all right, because if they lower this current, they can increase this voltage and keep the transmitted power the same. Remember that transmission power is a product of I and V. So if I lower I and then I increase V, I can keep PT the same. So yeah, I've just indicated examples here. So if I have this current and then I double the voltage, I'll still have IV. If I divide the current by, if I reduce the current by a factor of K and I increase the voltage by a factor of K, I still get IV. So this is very interesting now for transmission powers, because again, this is what they do. Of course, we know that the answer is B. Alternating voltage can be stepped up and stepped down, and this is what I'm explaining here. So I can transmit the power at very low currents and then very high voltages, so that the wasted power along the lines is very small. Why? Because the current is very low. But when I get to the community, I need a transformer that is able to regulate that the voltage is too high for consumers to use. So what do? They need to step down that voltage. So transmission agents, all right, or agencies, power transmission agencies, pretty much use alternating current because of this ability to regulate the voltage. I can step up the voltage, step down the voltage at the consumer's end, all right. So yeah, B is the answer. Ooh, and then there's this question. Figure 2 shows 3 forces acting at a point. The resultant force is, okay, listen, this one had a little bit of problem. So this angle is actually 125, right? So we have to, a candidate who actually draws these reference systems like this, because to resolve forces you need reference systems. If you draw vertical and horizontal reference systems like this, you're never going to get this problem right. Why? Because you don't know the angle each one of these forces make with these reference systems, right? You don't have enough data to get that. All right, look at this. This 60 Newton force makes a tiny bit of angle with this x-axis. How do you get that angle? You cannot. So what you need to do is you need to draw a reference axis from a particular force. So if I read through these alternatives, you notice the examiner is talking a lot about the 60 Newton force. So what I have to do here is that I have to wipe this off and then draw a reference along the 60 Newton force. So this 60 Newton force is my x-axis and then my y-axis somewhere here. So these guys have to be perpendicular to each other. We understand that. Now we can solve the problem. Let's solve the problem. We need to resolve each one of these forces. So there's a 30 Newton force, there's a 40 Newton force, and then there's a 60 Newton force. The 30 Newton force, guys, come here. The x component would lie along this direction. Now notice that these guys like this are perpendicular. Okay, if this is 125, you're going to take 125 minus 90. It's going to give you 35. So this tiny angle like that is 35. And if you come down here, this other angle, because these two guys are perpendicular, this angle has to be 55, right? Because it has to add up to 35 to give you 90. So this is 55. Am I getting it wrong? That's 35. This is 55, huh? Yes, this angle is 55 because 125 plus 55 gives you 180, right? Yeah, this angle is 55 here like that. So if I get this 55 here, this actually means that, well, I can resolve this force as 30 cos 55 along this x direction. If I don't want to use this cos 55, of course cos 55 is the same as sine 35 because they are complementary. That's why you see me using 30 sine 35 here, or you could say 30 cos 55. So if we use 35, it means that the y component will just be 30 cos 35, all right? Because this is 35 here, you resolve it along this y-axis, you have 30 cos 35 there. For the 40 Newton force, you just need to deduce what is this angle. These two guys like that are perpendicular. This is 90, so this has to be 10, so that all of this angle is 100. So you resolve along, you would have 40 cos 10, which is the y-axis, all right? Negative 40 cos 10. Why? Because it's going opposite to your actual y direction. And then you have the horizontal guy, which will be what? 40 sine 10. All right, so it's going the positive x direction, just like this our guy, so they are positive. But the 60 guy will be going the opposite direction. That's why you have negative 60 here, and then it's not going to have any vertical component, so you have 0. If we add this x and y components, we are going to have this result. Now we can go over and then say resultant force is of course the square of the y and the x coordinates, components squared and added, square root. So you get that, and then you get the result as 38.8, and then you get the angle, which is tan inverse of the vertical over horizontal, and then that gives you 22 degrees from the 60 Newton force. So you notice that our answer has to be D here, 38.8, 22 degrees from 60. Assuming the charge on the electron is this, the number of electrons hitting the screen of a TV tube each second when the beam current is 1 milliampere is, okay, this one is a giveaway question. So here is NE, which is equal to IT. So it means that NE is IT. So that means that our N over T, which is the number of electrons striking per unit time, would just be I over E. So our I is 1 milliampere, our E electronic charge 1.6 times 10 to the negative 19. That gives us 6.25 times 10 to the 15 electrons per second. So the answer here, this coulomb here is not the right unit, okay? The electrons per second. So our answer is A. So you can just pause the video and then read the question. All right, like I'm so out of time now. So we're going to make, once we get the unit of this K here, so we're going to of course make K the subject, square both sides, and then simplify, make K the subject. K is that this mg here is a force is kilogram meters per second squared, and then down here you have velocity, which is meters per second, all that squared, and then multiply by area, which is meters squared, and then density, which is kilogram per meter cube. And then you have the units to be 1, all right, because they basically cancel. Take note, simplify it, and then you notice that K is 1. So our answer is C. All right, so which of the following comparisons of various fields is not correct? All right, so which is not correct? So we have to pick out the ones that are correct first. Direction of the field line, okay, for gravitational field from test mass towards the planet, correct. Okay, that is the whole point of your weight. All right, so it's from I-axis from you, all right, towards the planet. Are we together? So where does your weight act? Your weight acts on you, while the reaction force to your weight, which it is, the reaction force to your weight is not normal reaction force. It is the force, the gravitational force you intend exert on the earth. All right, so yeah, that acts from you, so it acts on the test mass towards the planet, correct. Now electric field move from positive to negative charge, correct. Magnetic, you from north pole to south pole, correct. Now we have field set up by the body. Of course, it's set up by a massive body, correct, like the planet. Set up electric here by electric charge, correct, like a positive charge or a negative charge. Magnetic, of course, a magnet or current carrying wire, correct. So a current carrying wire would create a magnetic field around it, which the direction of the magnetic field around it is indicated by what? The right hand grip rule, all right, or the Maxwell corkscrew rule. So we have your thumb points in that rule. Your thumb is pointing in the direction of current, and then your fingers coil around in the direction of the magnetic field. So C says field acts on, well, for gravitation, test mass, correct. Test charge, correct. Magnet or wire carrying current, correct. So A, B, C are already correct, so D has to be the wrong answer. So possible to prevent a planet from acting on a test mass, not possible. This is shielding. So you can shield the electric and magnetic field, because for a north pole I can bring in an opposing pole, all right, so that it shields the influence of that north pole on a particular maybe compass, all right, exactly. So if I can counteract the effect of a particular pole or of a particular charge, then I can shield the effect of that field. But I cannot shield the effect of a gravitational field, because any object you bring also has a mass, and then in turn exert a gravitational force on another object that has mass. All right, that's why we cannot shield gravitational fields. So our answer here is D. A power beam of monochromatic light of wavelength 500 nanometer is incident normally on a diffraction grating. The grating has 600 lines per millimeter. The maximum order of diffraction, excluding the central bright fringe, is okay. So d sin theta equals m lambda. That's a famous diffraction gradient equation. So m, number of orders, is d sin theta over lambda. So sin theta is, we want to get the maximum order, so sin theta has to be maximum. So sin theta is 1, right? So m is d over lambda. So you notice that, well, our d is 1 over a, which is diffraction gradient specification. So 600 lines per millimeter, we have to reciprocate that. So we are going to have d as 1 all over that, 600 times 10 to the power 3, so that we now have lines per meter, okay? So we can now go over and then say, all right, our m, this is our d. So we have d over lambda, so all of this is our d. We put up here, lambda is this, we simplify, we have 3.3 but remember the examiner says we are excluding the central bright fringe because this order simply corresponds to what the order 3, because of course order belongs to Z. So 3.3 is not in Z. All right, this decimal part means that this guy is not in Z, so we have to take it off and then maintain 3. All right, so this means that if we're excluding the central bright fringe, the fringe system shifts and M1 becomes M0, and the system now has one less fringe. All right, because we're excluding that central bright fringe, so there are going to be 2 orders now. So our answer is A. Okay, so you're just going to pause the video and then read the question. All right, so heat supplied is of course the amount of work your kettle does in converting electrical energy into heat energy so that the content in the kettle can absorb. So the heat supplied would be power times time. All right, so power is that 3 kilowatts, and then your time is 15 minutes. You convert that to seconds, and then you plunge that. So you have the heat supplied by the kettle to be this. Now you can go over and talk about the heat absorbed. Okay, so the heat absorbed, WA, is actually going to be now you're heating that water, so the water has to change temperature from 25 all the way to 100 degrees Celsius, where it now starts to boil. So you first of all heated the water to 100 degrees Celsius, then you now change the state of the water. Okay, so we can go over here and then realize that, well, all of the water is changing temperature. So 1 kilogram of water has to change temperature from 25 to 100. So you put that in there, and then but only 0.6 kilogram of the water has evaporated. So only 0.6 kilogram of the water has absorbed latent heat of fusion, or of vaporization, sorry. So you realize here that, okay, if 0.4 kilogram is left in the kettle, okay, so 0.6 must have absorbed this latent heat of vaporization. So you put that in there, and then you do the math, and then you see heat absorbed is 1.67 times 10 to the power 6. There's a discrepancy between the heat supplied by the kettle and the heat absorbed by the content of the kettle. That tells you that the efficiency of the kettle is not 100%, right? Of course, according to second law of thermodynamics, we cannot get a heat engine whose efficiency is 100%. So wasted energy would be what? WS minus WA, supplied energy, minus absorbed energy or useful energy. So our wasted energy is going to be 1 million joules. Imagine all the electrical components you are using in your house, and then they are wasting 1 million joules of energy, like every time you use them for 15 minutes. That means that you're paying bills to an AO that you don't even get to use, right? So you're paying for wasted energy, you're not paying for used energy. All right, so they have to be grateful that you're paying for every single form of energy that is wasted instead of them accounting for it. All right, let's go on. So efficiency is of course useful work output over work input. So useful work output in this case would just be the heat absorbed by the content in the kettle. Work input would be the heat supplied, right? So the efficiency here would be 61.9%. I've done all of this work so that people can really get to appreciate the beauty of these things, but clearly the answer here was just the examiner just needed you to calculate the heat supply. So your question already ended here like this. So the answer was 2.7 times 10 to the power 6, which is D. All right guys, thank you so much for watching the video. I hope you enjoyed it. Please like, share, comment, and if there's anything you want us to do next, please let us know. Also, to check the original, check our website on the comment section below. You can also check our Facebook and our other social media handles or profiles so that you can follow us on other platforms. Thank you so much for watching. We'll be grateful if you can share the content with your friends or your state chiefs. A huge shout out to the people that are working with me on this video production process. Jana Hone, there is Bradford, oh what a lovely man, and then there's Princely. Thank you guys so much. We are a wonderful team of people trying to make sure that we give you the best YouTube content that is possible. All right, your comments, your feedback would be appreciated. Keep looking up, never stop being curious.